Where we left off on Monday, we were talking about the law of multiple proportions, and we talked about um what that is, like the definition. If you have a mass, fixed mass of one atom in a compound, and that those two atoms together can make multiple compounds. All of your other compounds, when you compare the masses of the second atom, that should give you some small whole number ratios. So we talked about how we had an example here where we had the mass of oxygen combined with 1 gram of nitrogen. So in this particular case, we had the fixed mass of 1 gram, and we know that the compound was NO something. And so we know that and we had numbers, the ratios or the mass numbers of the oxygen, and we took those data and we compared those mass numbers to see if this compound actually followed or if the data followed the law of multiple proportions, which it did. And one of the key things that we got from this example is that if you come up with a decimal, and you come up with a decimal here as one of your numbers in your ratio, you can make that into a whole number, right? So in this case, it was 2.5. So we just multiply the top and the bottom by 2. Down here, it was 1.25. And so we just multiply the top and the bottom by 4. So this is the ratio that we got, 5 to 4. And up here, 5 to 2. So a small whole number ratio. So let's do another example with this law of multiple proportions. Then we're going to move on to another topic. Uh, and then, of course, we'll work some of these tomorrow in recitation. I got a couple of good ones that we're going to work in recitation. Right. So let's look at this this other example. And today is February 2nd, 2022. All right. So the example here says you have 100 grams of two different compounds. Right, composed of sulfur and oxygen. Right, first compound contains 50 grams of sulfur. All right, and the second compound has 40 grams of sulfur. So the question is to show how these data illustrate the law of multiple proportions. So let's do that. I'm just going to abbreviate law of multiple proportions as LMP. All right. So the strategy, again, is we want one of our two elements that make up, or two atoms that make up that compound, to be 1 gram. That's our strategy. So we need to have a fixed mass of one or the other. So if we take the data or the information from the problem, it says that we have a sample of 100 grams for two different compounds. All right. So each sample is 100 grams. And then it says one of the samples has 50 grams of sulfur. The other one has 40 grams of sulfur. So let's take that information and use it to our advantage. So for compound 1, right, the mass ratio is 50 grams of sulfur. It's 50 grams of equals 50 grams of oxygen, because the total has to be 100. Does that make sense? Are y'all following that? So if it gave us 50 grams of sulfur and it said the sample is 100 grams, then the other atom, there has to be 50 grams of that. So the total would be 100. Right. So if we divide both sides by 50, then it's 1 gram of sulfur equals 1 gram of oxygen. Yes, no.
Yes, sir.
All right. And so let's do the other side. Let's do compound 2. It says we have 40 grams of sulfur. And that would mean we have 60 grams of oxygen, because again, it has to add. The problem told us that we have 100 grams of each sample. So that's 40 grams of oxygen, sulfur, 60 grams of oxygen. If I divide by 40, so this is 1 gram sulfur equals 1.5 grams oxygen. All right. So now we have our ratios that we can compare, right? And since sulfur is 1 gram in both, right, we'll compare oxygen. So this is going to be 1 gram and this is going to be 1.5. So let's make that into a ratio. So the ratio of the second atom, which is what the law of multiple proportions deals with, is you have a fixed mass of one atom in a compound, and then you look at the second atom, and when you take the ratio of the atoms of all the compounds that these two atoms can make, that second atom, when you take ratios of one to the other, it ought to be a small whole number ratio. So here we can say that the ratio for oxygen is 1.5 to 1. That's, again, we got a decimal, so we need to change that into a whole number. So we multiply top and bottom by 2, right? So let me highlight that. We'll make that a whole number. So we multiply by 2. So then the whole number ratio is going to be 3 to 2. And that does give us again, a small whole number ratio. So it does follow the law of multiple proportions. All right, any questions about this example? Because we attacked the examples that we've done, we've actually looked at this from multiple angles. We looked at it from, if we're given the ratio or the mass numbers, can we find the ratios? We looked at it where we given a mass, can we discern the mass of the second atom, which was this example, and then compare the ratios. And then we did it basically in a more direct fashion, where we actually took two compounds that were possible, and then we compared everything there, and then took the ratios of the second atom, and then we found that the ratio was a small whole number ratio. So we did that with the example with carbon monoxide and carbon dioxide. All right. Any questions about anything so far? All right. So with that being said, we're going to move to another topic. So we looked at the law of constant proportions, the law of multiple proportions. We've looked at talking about composition. We've talked about like how these laws were developed. We talked about atomic theory and how atoms and elements come together to form compounds. And these laws of constant and multiple proportions deal with atoms coming together to make compounds, right? That's what that's dealing with. And it's basically, the universe would not be what it is unless these atoms came together in these specific ways. And you can measure it, and it's the same all the time, right? So that's how you're able to develop a law, because every time an experiment was done to find out if something had a constant proportion, it did. Every time experiments were done to find out if the other compounds, if you compare the ratios, they always came out to be small whole number ratios. So that's how the law of multiple proportions was developed. So now let's go into, we're gonna get into a little bit more nuts and bolts about atoms and their components and subatomic particles and things like that. Excuse me. So let's jump back into here. And we're going to talk about the evolution of atomic theory. Right. So there's some kind of subtopics here that we're going to cover, and we're going to talk about some breakthrough moments. And we're going to talk about those breakthrough moments and those early results. And then we're going to start talking about the subatomic particles. Right, and how those were discovered, and then isotopes. So for this section, it's isotopes and average mass. The particles that make up the atom, and then some really like groundbreaking discoveries as far as like atomic structure is concerned. All right. So the first discovery that we're going to talk about is the discovery of the electron. All right. So the electron, we know, is one of our subatomic particles. And, you know, we talked about this in the last chapter, talking about atoms being made up of protons, neutrons, and electrons. But that had to be determined, right? Somebody had to experimentally prove that. And initially, everything is a hypothesis until you do the experimentation to actually prove that what you say is legit, right? That's the very first thing we talked about, is how hypotheses are just based on observation, empirical observation, but you haven't done the work to actually prove it. And then when you do the work, then that hypothesis can become a law. And then when you do more work and it never changes, and you are able to explain natural phenomena with those data, then it becomes a theory. So the person who was credited with discovering that there was some particle in an atom that helped to compose the atom was J.J. Thomson. Right. So what he discovered was that atoms were composed of smaller particles. And let me pull up, I want to pull up his device or his apparatus that he used to prove this. Right. So what J.J. Thomson, what his experiments were able to prove was that, and even his experiments, what he discovered, in that the atoms had to be composed of smaller particles, he didn't really understand what he had, right? But he saw an observation, and it made sense to him that either the atom was divisible, which is, you know, historically has been not the case, right? That's the whole idea, is that an atom is the smallest part of an element, and you can't go any further than that. but the atom is not necessarily divisible, but the atom is made up of other particles. So what he found was that electrons were about 1/1000th the 1/1000th times the mass of an atom. All right. What he also discovered was that atoms has smaller particles. That composed it, right? Out of all of his work. Now I want to pull up the book right quick and show you um the apparatus that he used. He used what's called a cathode ray. And I'll show you that. Hold up. Let me get, come on, computer. It's coming up. I'm gonna share my computer screen. So this is his device, right? And he had a magnet here to kind of work on separating the charges, because you know that atoms are composed of both positive pieces and negative pieces. He didn't know this at the time, but he had a magnet here. He had a cathode and an anode here, and he applied voltage. And what he noticed was that when he applied voltage, uh, that there was a beam that came from here, what he called a cathode ray. This was really heavily studied during the time. You can see this is 1897, right? That's a long time ago. And so what he found out from that beam was that there was some particles, charged particles, that made up that beam. And what he eventually found out was that those charged particles were electrons, right? He called them corpuscles or something like that. And so when he found that out, and found out that the beam had a negative charge, that led to the discovery of the electron. Because remember, atoms are made up of protons, neutrons, and electrons, and they're held together because the proton and the electron are attracted to one another. All right. What he found out was that this beam was composed of negatively charged particles, and that the particles were very light. And so another part of this discovery happened when Robert Millikan did what's called an oil drop experiment. And he found out that uh, he actually determined the mass of an electron. So let me show you his device, which is here, and then we'll go back and talk about his discovery. So this is the device he used right here, where he sprayed these oil droplets into here. And then what he was able to find out was the charge on the oil droplets and the mass of the electron. So let me go back to the notes page. Right, and again, let me do this too. I'm gonna take this this link and put it in the chat, because I think some of us may still not have this ebook. Again, if you can't afford the book that's in the bookstore, use the free ebook. It's the same information. It's just not bound, but you can actually download it on a Kindle and read it like that. All right, so Thomson, with the cathode ray, he found out that that ray was composed of negative particles, which later became the what we know as the electrons in an atom. And then with Millikan, right, what he found out was that there was a specific charge with this oil droplet experiment, right? What he found out was that the charge on the oil droplets in this experiment was always a multiple of 1.6 times 10 to the 19. So, and this is in coulombs. Right, so the charge was always a multiple of 1.6 times 10 to the minus 19. And what was found out was that this was the fundamental charge of an electron. Of one electron. Right. So he found the charge of an electron, and then he even went further and derived the mass of an electron, right? So that was a previously reported charge to mass ratio that was already reported in the chemical in the scientific literature. So he took this previous report and what he found out was that the electron had a mass of 9.107 times 10 to the minus 31. Sorry about that. Kilograms. That's nothing. That's like again 1/1000th of the mass of an atom. And I think the atom that they were studying was hydrogen. So that's like 1/1000th of the mass of a hydrogen atom. And this was derived from a charge mass ratio that had already been studied. So these are some important numbers. So 9.107 times 10 to the minus 31 is the mass of an electron. I'm gonna write that in down here. So that's the mass of an electron. This is the charge on one electron. Right. And the fact that the electron was actually discovered through experimentation is groundbreaking. It's groundbreaking because what it meant was that the atom and the way that we thought about atoms at the time, we were still developing and evolving. It was not set in stone like what atoms are. Well, not what they are, but how they're composed. Right? Because again, atoms were thought to be indivisible. Now you're not dividing this atom into other atoms, but you're dividing it into its components, which is really, really, really important. Uh, and I thought about that. Even the cathode ray that Thompson was using, it made me think about the movie Ghostbusters. How many of y'all seen that? Anybody seen the new one, like Afterlife? I thought that was a pretty excellent movie. It stayed true to the original, but that the whole idea behind that proton pack that they used to zap ghosts probably came from this cathode ray of electrons. They just changed somebody. They had probably some science consultant just change it over and say protons instead of electrons. Uh, but yeah, it just really was really interesting to see that. So now we know about the electrons. There were other experiments done because now we're getting to the point where we can develop a model for the atom. So you had a couple of models that existed, and this is all in the book. So don't so you had a model where the protons and electrons existed together, like this, and then you had another model developed by Japanese scientists that looked like this. This is before the discovery of the neutron. This is the Saturn model. And this is what's called the plum pudding model. Because the scientist that developed that model, he was British, and they ate plum pudding, where it was like this kind of like bread pudding with raisins in it. So the raisins were um, considered to be the electrons, and then the bread around it, or the raisins were considered to be the positive part, and the bread around it was considered to be the electrons. So, and then with the Saturn model, you had a positive charge here, and then a negative charge in the ring around the atoms, the atom itself, right? So this was developed. This is developed by Hantaro Nagoka, and then this was the plum pudding model was also Thompson's idea, right? So the actual what we know now is that the actual structure of the atom is closer to the Saturn model than it is to this plum pudding model. Like the electrons are away from the protons and they orbit the nucleus, but they're not in the nucleus, right? So there was another groundbreaking experiment, and this was done by Ernest Rutherford. And with Rutherford's experiment, he discovered a proton, which is a part of the atomic nucleus, right? It's heavy. It actually, along with the neutron, makes up the bulk of the mass of the atom. And he did an experiment using alpha particles, or these positively charged. And I'm gonna show you his experiment as well. Uh, and he did an experiment using alpha particles and gold foil, right? And based on the fact that some of the alpha particles got deflected, that made him understand that there was some kind of collision happening between the atoms of gold and the alpha particles that they were exposed to, right? So what he found out was that he discovered again the proton, or the positive part of the nucleus, right? And then in addition to that, it was also kind of discovered that electrons occupy the most space in an atom, right? So the model for the atom was now coming more into focus. So let me switch over and show you his experiment. He did this experiment again with gold foil, and I thought it's really cool. Let me find this. Let me find this right here. Simulation. I'm gonna pull this up. This is so cool. Um, and so this is. Let me slow this down too, so we can see it. So the alpha particles. This is the gold foil here, and the alpha particles were beamed in again. These are positively charged particles. They were beamed in, and so what this helped scientists to understand was that there had to be something in the atom that was heavier than an electron, right? Let me zoom in on that too, because the electrons were so light that there's no way that they should have been able to deflect these alpha particles. So what you see around the gold, the moving pieces, are the electrons, but the deflection happens when the alpha particles hit the nucleus of the gold atom. And you can see that every time one of those alpha particles hits that nucleus, it gets deflected. And so the only particles that get deflected now are the ones that hit a nucleus, right? If you notice, the particles like here that don't touch, that are passing by the electrons, they don't get touched. But if it hits a nucleus, then and gets deflected, then you see that, and you can pick that up because they have this zinc sulfide screen over here that change colors whenever the particle whenever a particle touches it. So what they determined was that although it was a small percentage that was deflected, they understood that that particle that being deflected was about 8 times 10 to the third times heavier than an electron, right? And that's how the proton itself was discovered. So it had to be something in that atom that was heavier than an electron, that was heavy enough to cause this deflection to happen. All right, so let me go back to here. Let's switch back over. Right, so Rutherford's experiment again helped to crystallize like the fact that there was something in the nucleus, and most of the mass of the atom existed in the nucleus. So your atomic mass is highly concentrated in the nucleus. The electrons are like very light, and whatever was in the nucleus, what he discovered what was about 8 times 10 to the third kilograms times, not kilograms. Right, 8 times 10 to the third times heavier than an electron. So the nucleus makes up the bulk of the mass of an atom. It's fully positive. Right? Think about the fact that if the nucleus wasn't positive, then there would be no deflection. But like charges repel one another. So these positive alpha particles hitting that nucleus and being repelled meant that they were coming into contact with a charge like themselves. Right. So all of these uh, little pieces of data came out of this Rutherford experiment. And what was one of the overall outcomes was the discovery that atoms are neutral, right? They don't have a charge. They have electrons, they have neutrons, and they have protons, but the protons and electrons are in the same amount so that the charges are neutral. All right. Any questions? All right. So one other subatomic particle that we had to talk about. We talked about how the electrons were discovered, how protons were discovered. But we haven't talked about the neutron, which is the other particle that's critical to the atomic structure. All right. So in order to talk about the neutron, we got to talk about isotopes. And isotopes, right? This is a discovery that was made by Frederick Soddy, and so he was studying radioactive ores of radium, and what he initially found was that there were two species that had they were identical in every way, but they had a different atomic mass, and so he developed this concept of what we call isotope, right? Same element, but it has a different atomic mass. All right. And so him studying these isotopes of radium led to some further discoveries. And in 1932, a long time ago, James Chadwick came up with the idea of the neutron. Right. So the neutron is similar in mass to the proton. I think protons and neutrons have roughly the same mass. Right. So the proton and the neutron have roughly the same mass, and they make up again the bulk of the mass of the atom. So the discovery of the neutron actually uh, helped to define what the isotope is and what these discoveries actually meant. So you have an element, and then you have another element, and they're identical in every way except for their atomic mass. And so the neutron helped to explain why that is, right? And so the idea behind isotopes, again, you have the same element, but a different atomic mass. So the mass changes because there are more neutrons in the nucleus, right? So an isotope, right? It has more neutrons in its nucleus, and thus it has a higher atomic mass. All right. So now we know about our three subatomic particles. We know what a proton is. It's a positive subatomic particle found in the nucleus. We know what an electron is, a negative subatomic particle that orbits the nucleus. And we know what a neutron is. A neutron is a neutral, has no charge, uh, but it's also a subatomic particle that's found in the nucleus. And I need to indicate that here. Right? It does not have a charge. It has a charge of 0. All right. Questions about anything? I know that was a lot, but are there any questions about anything? All right. So we're going to shift gears and move into um, atomic structure and symbolism. That's the next section in this chapter. But in 3 minutes, I don't want to start and then have to quit, but I'll give you the outline of what's coming, and then we can just kind of pick up on Friday, because Thursday, of course, we'll have recitation. Uh, so this is an entirely new section. Come on, we'll just move this to a new page. All right. So in this section, we're going to learn about atomic mass, atomic number, and charges. All right, so we're going to learn about that. We're going to define what the atomic mass unit is finally, because we've been looking at AMUs and all that stuff without having actually a concrete definition of that. All right, so AMU and also the average atomic mass. Right, because what the number you see on the periodic table for the atomic mass is actually the average of all the isotopes for that atom that exists, right? And then we're also going to calculate that average atomic mass. Very simple calculation. Right, but again, we'll pick this up on Friday. Tomorrow we'll have recitation, and I'll upload that handout to Blackboard later today. I just need to make a note so I don't forget. But with that being said, we're going to stop here, and